In example 4, let A be the area under the graph of f of x over 2 to 4. Compute A, the area, as the limit as n approaches infinity of the sum r sub n. First, we will find delta x, which is equal to b minus a over n. B is the ending point of the interval, so in this case that would be 4, and a is the first part of the interval, so that is 2. 4 minus 2 over n, so 2 over n is delta x. Recall that r sub n can be found by taking delta x times the sum from 1 to n of f of a plus j delta x. So in our case, r sub n is delta x, which is 2 over n, times the sum of f of a, in our case, is 2, plus j times 2 over n, j times delta x. So we'll write that as 2j over n. And this is our general term. And we're going to simplify the general term by using f of x. 2x squared minus x plus 3. So if we are evaluating f of 2 plus 2j over n, then each input x will be replaced with 2 plus 2j over n. So first we'll do 2 times the input squared minus the input plus 3. Our next step will be to expand and combine any like terms. So a binomial squared is the first term squared plus 2 times the first term times the second term. So 2 times 2 times 2 times j over n plus the second term squared. So 4j squared over n squared. Let's distribute this negative. Now distribute the 2. 8 plus 16j over n plus 8j squared over n squared minus 2. I'm going to write this in descending order, so 8j squared over n squared will be my first term, plus 16j over n minus 2j over n is 14j over n, and 8 minus 2 plus 3 is 9. This is the simplified version of our general term. So now we can use summation notation and linearity to help us simplify. I will use linearity to further break it down by saying, okay, 2 over n is going to be multiplied by each sum, but I can take the sum of each of these 3 terms individually. So I'll have 2 over n times the sum of the first term plus 2 over n times the sum of the second term plus 2 over n times the sum of that third term, which is 9. Because everything inside of each summation is a product or quotient, I can factor out any constants or anything that's not dependent on j. So in this first one, I can actually factor out 8 over n squared. So this would be 2 over n times 8 over n squared times the sum from 1 to n of j squared. And in front, we will simplify this to 16 over n cubed times the sum of j squared. Continue to do this for the other ones. We'll take out 14 over n, which will equal 28 over n squared when we multiply it by 2 over n. Now we're simply taking the sum of j here, and in this one, I know in our last video I did not factor out when it was just a constant here, but the textbook did, and so I'm going to do that, see if maybe that helps some of us visualize it better. That would be 1. So 18 over n times the sum of 1 from 1 to n. Now, in order to get rid of that summation notation, we can use our power sum formulas. And here we have the sum of j squared. And that power sum is n cubed over 3 plus n squared over 2 plus n over 6. So that's what we will replace this sum with. And j, here, taking the sum from 1 to n of j, we can replace that with our power sum formula here and get n squared over 2 plus n over 2. And lastly, we have a formula for linearity that states that if you're taking the sum of a constant from 1 to n, then your sum is just n times whatever that constant was. So we will replace this summation with n times the constant, and in that case our constant is 1. Our first summation is replaced with n cubed over 3 plus n squared over 2 plus n over 6. Our second one is replaced with n squared over 2 plus n over 2. And our third one is replaced with n times 1, which is n. We're going to distribute and combine like terms. 16 over 3 plus 8 over n plus 8 over 3n squared plus 28 over 2 is 14 plus 14 over n plus 18. Only your denominators have powers, so they didn't write it in any particular order. And really the order doesn't matter that you write it in, right? Because you're going to take the limit of that expression anyways. So let's combine our numbers. 16 over 3 plus 14 plus 18 is 112 over 3. You can check that with your calculator. 8 over n plus 14 over n is 22 over n plus 8 over 3n squared. Now we have a term we can calculate the limit. So the area is equal to the limit as n approaches infinity of r sub n, and that would be the limit as n approaches infinity of r sub n. Remember that this is r sub n, so plug that in. Here you can use quote direct substitution with your infinity because your terms are separated. That's the beautiful thing about using the power sum formulas. It makes it really easy to quote plug in infinity. Any number dividing infinity is equivalent to 0. So the area under the curve from 2 to 4 of f of x here is 112 over 3 units squared, I guess. For this example, we're going to prove that for all b greater than 0, for all positive b, the area A under the curve, under the graph of f of x equals x squared over 0 to b is equal to b cubed over 3 as indicated in this figure. And here we have one of our power sums that we will end up using. So let's begin by using r sub n that does tend to be the easier one to evaluate. First, I'm going to find delta x, which is equal to the end of the interval minus the start of the interval divided by n. And this would be b over n. So here's our right endpoint sum, and we will plug in delta x, which is b over n, times the sum of f of a is 0 plus j times delta x, j times b over n. Our function here is x squared, so I will take our input and plug it into our function. Now 0 plus anything is just the thing you're adding, so really we're taking j times b over n, and that should be squared. I know there are parts of this that I want to factor out, so I'm going to apply the squared, to each piece inside of this product quotient, and that would give me j squared times b squared over n squared. Nice. Now I can take the b squared over n squared out of the summation, factor it out. So I will have b cubed over n cubed factored out times the sum of, now it's just the sum of j squared. The sum of j squared from 1 to n, we have a formula for that. We have a power sum formula. And that formula is n cubed over 3 plus n squared over 2 plus n over 6. I'm going to distribute now, so I'll get b cubed over 3 plus b cubed over 2n plus b cubed over 6n squared. And now we will evaluate the limit as n approaches infinity of this beautiful r sub n term we have created. Let's quote plug in infinity, and when you do, you end up getting numbers or values equivalent to 0, which proves that the area from 0 to b of f of x equals x squared, the area under that curve, will be b cubed over 3.